Alan Turing was born in London on June 23, 1912, long before anyone carried a computer in a pocket or asked a machine to write, recognize faces, break codes, or make decisions. Yet the questions that shaped his life still sit underneath the modern world. What can be calculated? What does it mean for a machine to follow a rule? Can a machine appear to think? And what happens when a society depends on a mind it later punishes? Turing's story begins with mathematics, not with electronics. As a young scholar at King's College, Cambridge, he entered a debate about the limits of formal reasoning. Mathematicians wanted to know whether every true mathematical statement could, in principle, be proved by a mechanical procedure. Turing answered by imagining a simple theoretical device, a machine reading symbols on a tape, following rules step by step. It was not a gadget sitting on a desk. It was an idea precise enough to define computation itself. In 1936, Turing published On Computable Numbers. The paper showed that some problems cannot be solved by any rule-following machine, however patient or well supplied with tape. But the same argument also described a universal machine, one machine that could imitate the rule table of any other. That idea became one of the foundations of modern computing. Later computers would use electricity, memory, processors, and software, but Turing had helped make the boundary of the possible visible. Then war forced theory into emergency. In 1939, Britain entered the Second World War. German forces used the Enigma cipher machine to protect military communications. Enigma did not simply scramble words once. It used rotors, plugboard settings, and daily keys to create an enormous number of possible encryptions. Breaking those messages required mathematics, engineering, captured material, disciplined procedure, and a large organization able to turn fragments into intelligence. Turing arrived at Bletchley Park, the secret code-breaking center in Buckinghamshire. He was not alone, and the story should not be told as one man solving the war by himself. Polish cryptanalysts had made crucial pre-war breakthroughs. British codebreakers, engineers, wrens, linguists, clerks, intelligence officers, and military users all mattered, but Turing's contribution was central. He helped design methods and machines that could search Enigma settings at a speed human hands could not match. The British bomb was not magic. It exploited weaknesses, likely words, and logical contradictions in German messages. Operators set up menus. The machine searched possibilities. When it found a promising stop, people still had to test, interpret, and distribute the result. Intelligence from Enigma, later called Ultra, helped Allied commanders understand U-boat movements, air operations, and battlefield intentions. Historians debate exact counterfactuals, but most agree that code-breaking shortened the war and saved lives. The work also carried moral pressure. A decrypted message was only useful if the enemy did not realize the system had been penetrated. Some information could be acted on, some had to be protected. Secrecy shaped decisions during the war and memory after it. For decades, many Bletchley Park workers could not speak publicly about what they had done. Turing's wartime reputation was therefore hidden from the public record at the very moment his post-war ideas were beginning to matter. After the war, Turing turned toward real electronic computers. At the National Physical Laboratory, he worked on plans for the automatic computing engine known as the ACE. The design was ambitious, fast, flexible, and built around stored instructions. Delays and institutional caution frustrated him, but the direction was clear. Computing was becoming less a room full of people doing arithmetic and more a general-purpose machine able to change tasks by changing instructions. Turing also moved from computation to intelligence. In 1950, he published Computing Machinery and Intelligence. Rather than define thinking in abstract terms, he proposed a practical test based on conversation. If a machine's answers could not reliably be distinguished from a human's, what would that say about machine intelligence? The imitation game was not the whole philosophy of mind, and Turing knew objections would come. But he reframed the question in a way engineers, philosophers, and the public still argue about. This is where the modern AI age often looks back to Turing. He did not build today's neural networks. He did not predict every problem of data, bias, labor, surveillance, or automation. But he asked a durable question at the point where mathematical logic, machinery, language, and human judgment met. When people today argue over whether systems merely simulate intelligence or display something more interesting, they are walking through a door Turing helped open. The personal cost of his life was severe. In 1952, Turing was prosecuted in Britain for homosexual acts, then criminalized under gross indecency law. He accepted chemical treatment rather than imprisonment. The conviction damaged his security clearance, limited his work, and placed the state's suspicion over a man whose wartime service had depended on trust and secrecy. In 1954, he died at the age of 41. An inquest recorded suicide, though some later writers have questioned details around the death. The safest statement is that the conviction and treatment were a profound injustice. Britain later acknowledged that injustice. Prime Minister Gordon Brown issued an official apology in 2009. Turing received a royal pardon in 2013. His image later appeared on the Bank of England £50 note. These gestures did not undo the harm done to him or to thousands of others persecuted under the same laws, but they changed public memory. The state that had punished him now held him up as a national figure of science, war service, and moral reckoning. The code-breaking story also shows the difference between information and power. A broken cipher did not automatically win a battle. Intelligence had to be trusted, compared with other evidence rooted through commanders and sometimes hidden to protect the source. Bletchley Park therefore belonged to a wider Allied system. Naval escorts in the Atlantic, radar stations, convoy planners, captured codebooks, direction finding, and people who translated mathematical possibility into practical action. Turing's genius mattered because it operated inside that system, not outside it. The computing story has the same lesson. Turing's universal machine idea did not instantly create the laptop, the server farm, or the neural network. It gave later engineers and scientists a language for general-purpose computation. Hardware designers, programmers, manufacturers, universities, government laboratories, and commercial firms turned that language into working machines. The value of Turing's abstraction was that it survived changes in materials. Whether the medium was paper tape, vacuum tubes, magnetic memory, silicon chips, or distributed cloud systems, the basic question stayed recognizable. Can this process be described as rules a machine can carry out? That question matters because computers became institutions, not just tools. Banks, militaries, hospitals, universities, police departments, studios, factories, and homes all came to depend on procedures made executable. In that sense, Turing's life sits near the origin of a modern tension. Rule-following machines can extend human capacity, but they can also concentrate authority, hide decisions inside systems, and make old injustices more efficient if people refuse to examine them. Turing himself was harmed by a legal system that treated his private life as a crime. His memory therefore warns against celebrating technical brilliance while ignoring the human rights context around technology. The imitation game also remains powerful because it shifts attention from a machine's inner mystery to its public behavior. Turing did not require a machine to possess a soul, a childhood, or a human body before it could be discussed seriously. He asked what would happen if its answers forced human judges to reconsider their categories. That move was both modest and radical. It avoided claiming too much, but it also refused to protect human uniqueness by definition alone. Modern debates about artificial intelligence still turn on that pressure. Performance, explanation, responsibility, and trust do not always move together. Turing's legacy is often simplified into a single heroic label: father of computer science, codebreaker, prophet of artificial intelligence. Each label contains truth, but each can hide the fuller story. Computing did not have one parent. Enigma was not broken by one mind in isolation. Artificial intelligence did not spring fully formed from one paper. Turing's importance lies in the way his work connected fields that had seemed separate: proof, machines, war, intelligence, secrecy, and the rights of the individual against the state. That is why June 23, 1912 still matters. Turing's life shows how abstract thought can become machinery, how machinery can alter war, and how a society can benefit from brilliance while failing the person who carried it. The machines of the present are faster, larger, and more connected than anything he saw. But the deepest issues are still recognizably Turing's. What can machines do? What should humans ask them to do? And what obligations do we owe to the people whose minds make the future possible?